Hi college algebra students, I miss you. This is our first video and we are going to be covering section 4.1. So this is the new packet that you would have gotten if we had come back after spring break. So this blank packet is on our Blackboard page. It's under content, under unit 4. There's also my completed packet under there with all of my notes on it. So you can always look at that if you need to. Okay, so this section covers exponential functions. And so we know that exponents help us to write repeated factors in a more condensed form. What you see here is an exponential function. So let's just go over a couple of pieces related to this. We know f of x is another way to write y. We know that b would be considered the base. It's the number that's being repeated. It's any positive constant other than 1. And the exponent in this case is our little x. And the exponent is just how many times the base is repeated. And it can be any real number. So this little guy right here, this b to the x, is the base and the exponent. Now our coefficient in this case, and that's what we're talking about here, is the number in front of the exponential term. It is not raised to the power. So in this case, because we don't see anything, it's just a positive 1. Okay? Now, here's the difference in a regular exponent term and an exponential function. In an exponent term, you can have any base and any exponent. In an exponential function, the variable must be in the exponent. So this time, your exponent has to be the letter or the variable, which is not what you are used to normally in math. So first thing we're going to do is look at these 4 examples and ask ourselves, is it an exponential function? Well, when I look at the first one, this is the term with the exponent, so this is the one that I'm looking at. I have a base of 3 and an exponent of x. And since the exponent is a variable, yes, this is an exponential function. I go on to the next one. Here's my term with my exponent. And by the way, these are all functions because they're all equaling f of x. But this is not an exponential function. Yes, it has an exponent, but the exponent is a number and the variable is our base. So in this case, no. So the key is the variable must be in the exponent. That's the key. Okay, we look at our next example. Here we go. Here's our term with an exponent. But again, this is not an exponential function because our variable is the base and not the exponent. Okay, now this one down here is a little tricky. This is something you may not have seen before. We have a base with an exponent, and then our exponent has an exponent. And so in this case, this is an exponential function because x is an exponent of the base 5. And so since he is part of the exponent, he is an exponential function. So again, the key is the variable must be in the exponent. Okay, so now let's talk about a base that is used quite a bit, and that is the letter E. He's actually a number. He actually stands for this never-ending number that goes on forever. We're just going to approximate him and just say that he's 2.718, and then of course those are the dots that says that he goes on forever. He's really important. E to the x is known as the natural exponential function. Now you can find him in your calculator. If I look at, here's my graphing calculator. I don't have an example of your smaller scientific calculators, but you can find him there too. He's normally hanging right around one of these 2 buttons, so either the log or the ln button that we're going to talk about in another section. But if you look on the graphing calculator, here he is, he's e to the x. So if I turn on my calculator, In order to get him, I would have to do second ln. And then there he is. He pops up right there. And so if I just were to put e to the 1, there you have the entire, well, not the entire, because he does continue on and he repeats, but you do have e to, you know, a certain number of decimal places there, but that's how you access him on your calculator. So he should be around there somewhere, even if you have to hit the second button to access him. Okay, now for parts A through D, we're just gonna do a little calculator work. So first of all, in part A, we wanna find an approximate answer to this. We're gonna do 3 raised to the square root of 2. Okay, so the way that we would put this in our calculator is actually 3, and then most of you have that little caret button that helps you raise something to another power. And then in parentheses, we're gonna do square root of 2 and close parentheses. So in my calculator, I'm gonna do 3. Here's my caret button. Now you notice I've raised up as an exponent. Okay, I like to put parentheses just to make sure that everything's where it's supposed to be. You probably don't have to have those, but I like to do it. Okay, now I'm gonna put in my square root button and 2. I'm gonna scoot over, close my parentheses, and there's my answer. Okay, if you don't have this little caret button, this little triangle without a base, sometimes you will see a Y to the X button. And so in that case, that also lets you be able to put an exponent onto any number. Okay, so you notice here that we have a nice little approximate answer. So I'm gonna do a squiggly equal sign there of 4.7288. I'll just leave it at that. Okay, all right, let's try our next one. Okay, so I'm gonna do 8. I'm gonna use my caret button and raise them up. Now I have an exponent. I'm gonna put in parentheses a negative, so remember, not your subtraction sign, but a negative 1.7, and I'm gonna close it and hit enter. Okay, now again, we have a nice little approximate 0.0292. Okay, I just rounded it to 4 decimal places. Now you don't have to use that approximate equal sign. You can just write a regular old equal sign if you want to. I'm just doing that because we are rounding. All right, now let's try out that E button. Okay, so I'm gonna hit second until I can get the E to pop up. All right, I don't even have to hit the caret because look, it automatically expects you to have an exponent on that. So I don't need to do that. I'm already up there. I'm gonna put in a 1.9. You can use parentheses or you don't have to. And we end up with 6.6859. Okay, and last but not least, let's try that E again with a negative exponent. So I am going to use parentheses since I'm using a negative, and again, negative, not subtraction. 0.06, close your parentheses, and look at there. When we used a negative exponent on the little e, we ended up with a number smaller than 1, and we got 0.9418. So you will be asked to use E, to use the caret button. You'll be asked to do various exponential functions or exponent terms in my math lab. So make sure you're comfortable doing that and you know how to do that on there. Okay, well now let's also talk about how would these exponential functions be graphed. Well, here is our b to the x. That's what we learned represents an exponential function. When b is greater than 1, we have a curve that looks like this. And it has a y-intercept right here at +1. Now, if we also take that b of x, but in this case our b is between 0 and 1, which means it's a fraction, still positive, but it's a fraction, it's going to give the same graph, but it's going to be flipped across that y-axis. Still giving us a y-intercept of 1, but that's what we end up with. Now that's important because we're going to do some transformations, and so we need to see what the original parent function looks like so that we can then transform it into other ways. Okay, let's turn to page 2. Okay, before we jump into these transformations, let's talk a little bit about the graph and some important information about the graph. So with both of those graphs, you may have noticed that our domain is all real numbers, because as we move from left to right, they are going from negative infinity to positive infinity. Even though they're curving up and they're continuing to move to the right. So our domain is all real numbers. Now the range is going to vary. Right now the range looks like it's just anything positive, right? Anything above 0, almost like the x-axis is an asymptote. But we are going to translate that, so it's going to vary a little. Okay, we already talked about that it could be 2 different graphs depending on our base. With the b is greater than 1, the graph increased. The greater the value of b, the steeper the graph. We talked about when the b was a decimal, we're decreasing. And the smaller the value, the steeper the decrease. We had an intercept at y equals 1 for both of those. No x-intercept because we never touched the x-axis. In fact, the x-axis is the horizontal asymptote, which is y equals 0. Okay, let's look at some transformations. We already know these transformations. So we know about the vertical and the horizontal translations. We know the reflection. We understand the stretching and the shrinking. Remember the order: horizontal, stretch or shrink, reflection, then vertical. Hippos seem really violent. Remember that silly little sentence helps you put it in the correct order. Now, here's the difference in some of these translations. Now, the vertical translation, which again, according to our hippo sentence, is going to happen last, is just as you would expect. You would have a constant added to the end of the entire function or subtracted at the end of the entire function. So that comes at no surprise. The horizontal translation, though, is a little different. It's hard to see the difference here, but this constant that's being added as we shift to the left is not added to the whole thing. It's added to just the x. So we have to take note of that. A vertical translation is added or subtracted at the end of the function. A horizontal translation is added or subtracted on just the x, which in this case is the exponent. So that's a little different. Okay, let's look at reflections. We know that with reflections, wherever the negative is, that's what we're reflecting over. It's the opposite of what you think. So here, in this case, the negative is in front of the entire b to the x, which means we're going to reflect over the x-axis. When the negative is just in front of the x, which in this case is the exponent, we're reflecting over the y. And then I'll let you look over the vertical and horizontal stretching and shrinking on your own there. My math lab takes care of that for you, so it's not something that you really need to focus on. Okay, let's turn our page then and look at example or page 3. Okay, so we have some options here, some graphs. And we want to be able to choose which one goes with which, okay? So here we go, 6 graphs, 6 exponential functions. Let's figure out which is which. Okay, well, let's start with this first one. F of x equals 4 to the x. Well, that 4 to the x looks a lot like b to the x. So, and if I look at every one of these, it appears to be this parent function with some transformations happening. So this must be the starting point. So what we're looking at, if you recall our original graphs, we're looking at a graph that uses the x-axis as an asymptote. It's going to increase, and it's going to have a y-intercept at 1. Okay, so as I look through these, The one that I see that resembles that is 22. This number 22 is going to be 4 to the x. Now, theirs looks a little different, right? Because they get really, really, really close to the x-axis. So it almost looks like they're touching, but they're not. And it's also really hard to see unless you count all 20 tick marks that this in fact is y equals 1. So there we go, that we have 4 to the x. Okay, so now let's try our next one. Now we have -4 negative x. Okay, well, let's figure out what's happening here. A -4 negative x. Okay, well, the negative that you see out in front there, okay, is going to be a reflection across the x-axis. Then the negative that you see in front of the x is going to be a reflection across the y-axis. Now, so these are both reflections. Which one you do first is up to you, okay? So if we're starting out with this parent function and I'm going to reflect across the x-axis, I'm flipping down, okay? So this is what I started with. If I flip it across the x-axis, this is what I have now, okay? So this would be -4 to the x. Now I'm going to reflect it across the y-axis. So now I'm going to take it and flip it this way. And when I do that, it just so happens number 19 represents that particular function. So I flipped over the x because of this negative out front, and I flipped over the y because the negative in front of the exponent x. Okay. All right, we go to our next one. I have 4 to the x. Well, great, that was my parent function, right? Like number 22. And then I notice a -1 on the entire thing. So a -1 on the entire thing means I am going down 1, okay? So if I am just taking what I see and moving down 1, I notice it's number 23. So if we wanted to make some little notes on here, I'm just going to write normal. That's our parent function for 4 to the x. For -4 to the negative x, we are going to reflect over y and x axes. I'm not really sure how you spell axes. We'll go with axis, and then you can just know there's 2 of them. Okay. All right. Then this one, we are moving down 1, and that was number 23. Okay, next. All right, this one is just the first step that we took over here with the capital H of x. So the capital F of x here just has 1 negative out in front, which means a reflection, and it's a reflection across the x-axis. And if you notice, we had done that here in our first step to getting the capital H of x. So this one is what we're looking for. Here it is. This is our -4 to the x. So this is going to be where we reflect over the x-axis. Okay, now we're going to look at this one. Now pay close attention here to this little g of x and the little h of x. Notice the difference in where the -1 is placed. When the -1 is in back of the entire function, we're vertically shifting down 1. When the -1 is just on the exponent, the x, we are moving it to the right 1. And so that guy is going to be right here. Okay, so when that happens, it gets a little confusing. We no longer have a y-intercept at y equals 1 because we have shifted that over a little more. So our y-intercept is actually much, much lower in that case. Okay, and then capital G of x, we have another reflection because I see that negative. And then because the negative is on the x, we are reflecting over the y-axis. Remember, reflections happen in the opposite way that you think that they should. So if we're starting this way and we're reflecting over y, we're just going to go the opposite direction, which happens to be number 24. And there we go. So I hope that kind of helps you think about the translations a little bit better. The down and the right, where you have the -1 on the entire function and the -1 on just the exponent, those tend to be the trickiest for students, but I hope that helps you a little bit. Okay, now let's do some of our own. So here we go. We want to graph this equation that they have given us. And we want to identify any asymptotes, the domain, and the range. Okay, well, as I'm looking at this, I'm realizing my parent function was just 2 to the x. So that's where I originated. This would have had a y-intercept at y equals 1, and it would have come from the left with an asymptote here at the x-axis, gone through the y-intercept of 1, and then shot up, okay? So let's put in our hippos seem really violent and figure out what exactly has happened here. So horizontal is the first thing I need to look at. Did something horizontal happen to our parent function? If it did, it would be added or subtracted to our exponent. And sure enough, I see a +3 here. So with a +3, I know that means left 3, okay? So that would be the first thing I need to do. So instead of having a function that we described that looked a lot like this one over here, just maybe a different steepness there, okay, I'm now looking at a situation where I am going to move to the left 3, okay? So this little point here that would have helped me shoot up, that would have been my curve, he's going 1, 2, 3. So I'm looking at something that looks a lot like that. It was just moved over there to the left 3. I probably should make him a little bit lower, a little bit more of an asymptote there, but that's what we're dealing with, okay? All right, so this went 1, 2, 3 with this y-intercept. I just kind of move it according to the y-intercept. Okay, so as I go back, I don't see any shrinking or stretching. A shrink or a stretch would have been right in front of the x or in front of the entire function, and I don't see that, so I'm going to cross through my s. Okay, now I move on to r. Any reflections? I don't see any negatives, so I'm going to get rid of that. I do see a +2 added to the back, which would be a vertical translation. And in this case, it would be up 2, okay? So now I'm gonna take my graph, okay? I'm gonna take my graph and I'm gonna move him up 1, 2. So whereas this would have been my curving point that you see here, it's now gonna get taken up here and it's gonna go like that. And so now we're looking at this. So we have moved up a little bit there. Okay, so now we have our graph. So this one ends with left 3, up 2. Okay, we want to identify any asymptotes. Well, this one always has an asymptote at the x-axis, the y equals 0, unless it's been moved. And so since we have shifted up 2, our asymptote is also going to shift up 2. And asymptotes are represented by a dotted line. You know I can't draw a straight line, but here's our nice little asymptote. So we are going to have a horizontal asymptote at y equals 2. It was at y equals 0. It has moved up to y equals 2. So this graph is actually going to come down a little bit lower like that. Okay? Now it wants the domain. Well, we already said that our domain is always going to be all real numbers, because even though it looks like this is sort of leveling off, like this is possibly even an asymptote keeping this in line, this is not. This is going to continue to move over toward positive infinity. So it's going to continue off just like a parabola would. Okay, now let's talk about our range. Okay, so our range, our graph doesn't really begin till about here. Now remember, y equals 2 is an asymptote. So this graph is going to get really close to y equals 2, but it's never going to touch it. So 2 is a boundary, but it's not a hard bracket because it's not going to touch it. It's a parenthesis. And then, of course, it's going to continue up to positive infinity. So no hard bracket, but it is bound right here at a positive 2 because of that asymptote. Okay, so you can kind of make the connection between these two numbers. All right, let's try our next one. Here is our function. Okay, so I'm looking at this, I'm kind of piecing it together, realizing that our parent function was 5 to the x. Okay, and it would have resembled this up here, just a nice little curve like that, increasing curve with an asymptote at y equals 0. Okay, I'm going to draw my little hippo seam really violent letters over there. Okay, I'm going to start with horizontal. Is anything added or subtracted to the exponent, indicating a horizontal translation? Yes, I have a -1. And a -1 in horizontal translation means right 1. Okay. So here we are going to move right 1. So instead of going through y equals 1 as my curve, we're actually going to go over a little further, which means that we are going to be going like this. That's what we're dealing with. We were shifted over 1. Okay. All right, now I'm looking for a stretch or a shrink, but I don't see a number in front of either one. I'm looking for a reflection. Yep, I see a negative right there. That negative indicates we are going to reflect over, because it's out in front, the x-axis. Okay, so if I'm going to reflect over the x-axis, I'm going to take the curve that you see and I'm going to flop it right over here, just as if I were to fold the paper. Okay, so this is going to indicate the end of the curve that was right 1 and flipped over the x-axis. So I'm going to just replicate this curve that I have right here, but it's going to end up being just like this. Okay, it's not beautiful, but I did the best I could there. I just flipped it right over the x-axis. Okay, and there's no vertical. I don't have anything added or subtracted to the end, so I just had 2 issues, just like I did in this top one. Okay, so horizontal asymptote. I didn't move vertically, so my horizontal asymptote stays the same as the parent function. It's the x-axis, which is y equals 0. My domain, all real numbers. It always is. Let's talk about reflections. Okay, I'm sorry, not reflections, ranges. Okay, so the range, I'm starting at the bottom and I'm moving up. I'm coming up from negative infinity all the way, these are y values, remember, for your range, to 0, but I'm never going to touch 0 because that is my horizontal asymptote. So it gets a parenthesis. So notice that the horizontal asymptote is always part of the range, always part of the range, but it also always has a parenthesis because you're never going to touch it either. It's the asymptote. Okay, so we have a few more pages here, 2 more pages in this section. All right, let's turn on over to page 4. Okay, let's look at our our e to the x function and talk about it a little bit. Okay, so e to the x, the whole thing minus 3, we're going to treat it like any other exponential function. That would have been our parent function, okay? So I'm going to go ahead and draw the parent function because as I'm looking over this, there's only one thing that happened to it, and I have 2 graphs, so let's just go ahead and use both of them. So this is going to be our original. This is going to be our parent function, our y equals e to the x. So it's going to come over here at y equals 1 and continue. And we have a nice asymptote over there, and there we go. Okay, we're going to make our letters for hippos seem really violent. I notice I have no horizontal translations. There's nothing added or subtracted to the x. There's not a stretch or a shrink. I don't have any numbers added in or placed in front there. And I don't have any negatives either, no reflections, which means only one thing happened to this graph, a vertical translation. And a minus 3 means down 3. Okay, so if that's what I do over here, if I go down 3 from my original, okay, I'm just taking what you see here and moving down. So I did have a y-intercept at y equals 1, and now I'm going to go 1, 2, 3, and I'm going to have a y-intercept at y equals -2 because I went down 3. Okay, so there we go. We have our graph. Let's talk about asymptotes. Remember, the horizontal asymptote is the next horizontal line right beneath that y-intercept. So in this case, your horizontal asymptote is y equals -3. Okay, so we had to draw that in. We knew it was there because this was our y-intercept, which means that the horizontal asymptote is just one step below. It's always one step below, unless it's been reflected, and then maybe it's one step above, right? It's always right there next to it. Okay, our domain, like always, is all real numbers. Our range, okay, we have to be careful here. We're coming from the bottom, we're moving up, 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 up. We're gonna take our horizontal asymptote, remember that's always part of our range, that's where we're going to start, but we're going to give it a parenthesis because we don't ever touch it. It gets really, really close, but not quite touching. And then we're going to put an infinity on the other side. And there we go. So we have covered exponential functions. Now there is one little piece left of this section, and that is compound interest. And this is a very important piece of this section. So let's talk about that. That's the last part, and then we're finished. Okay, let's talk about interest for a little while. So interest is extra money that is given to whoever lends out the money when it comes to a loan. So if you take out a loan with the bank, let's say to pay for your car or to pay for your home or to pay for anything, then the bank is going to let you have that money. They're going to lend you that money. But when it comes time to pay back the money, not only do you have to pay back what you borrowed, but you also have to pay back a little bit more. And this is called interest. How much interest depends on the interest rate. Okay, the interest rate. Now, we're not going to talk about that side of interest. We're not going to talk about what happens when the bank loans you money. We're going to flip that on its head, and we're going to talk about what happens when you loan the bank money. So you may have heard the expression that the rich get richer, okay? Well, how do rich people get richer? Well, they make investments. They make really great investments with money that they currently have that they do not need at the moment. They make investments with that. They lend it to banks. They lend it to different institutions. And then when it comes time to get the money back, not only do they get back what they put in, but they get interest from the bank. And so they make more money than they would have. So that's what we're talking about here. And we're not talking about simple interest, where you may just get back a flat amount. We're talking about compound interest. Now, compound interest means that you get some interest back and then you get interest on the interest. And then you get interest on the interest of the interest, and it just keeps building and building and building and building. And before you know it, you have really made a lot of money by investing in different opportunities with the banks. So that's what we're going to talk about here, because they can be represented as exponential functions. Okay, so two different equations. This is the equation. If you have a certain number of compoundings per year, now we don't know how many. Could be 1, could be 2, could be 12. We're not sure, okay? This is the equation if you have continuous compounding. So in the problem, if you see the word continuous, you use this one. If you do not see the word continuous, you use this one, okay? And of course, those will be given to you on your tests. Okay, so don't memorize them. Let's talk about what each of these mean. T, here it is, time in years, okay? A, which is normally what you're solving for, is the balance in the account at the end. It's how much you ended up with. P, that you see here, is the principal amount. That means the chunk you started with, okay? R is your rate that you're putting in. Now it's going to be given as a decimal. So they are originally going to write it as a percent. You have to change it to a decimal. So to go from a percent to a decimal, remember you divide by 100, or you can move your decimal point there to the right 2 places. Nope, just told you the wrong thing. To the left 2 places. How about that? Okay, so that you can figure out your rate. So please do not think that P is for percent. Not for percent. P is for principal. The percent is your rate, but you have to write it as a decimal. You're going to move it 2 places to the left. Okay, now that's it for this one. The only other letter is E, and we already know that's on your calculator. For this equation, we have one more variable. We have N. So for N, that means how many times a year are we compounding it? If they tell you we're going to compound it semi-annually, that means twice. For all you shoppers out there, you know, when they tell you there's a semi-annual sale, you know that they have a sale twice a year. Okay, quarterly, if it's compounded quarterly, we know that's 4 times a year. And if it's compounded monthly, that's 12 times a year. Okay. All right, so let's try this. Here we go. Okay. We just have this one example. Okay, one example here, and this will take care of all our questions. Okay. So I know it's a little hard to read. I copied it right out of my math lab, but here we go. Here are the 2 formulas. It doesn't tell you which one to use. You have to figure that out. Round your answer to the nearest cent. This is money, so we need 2 decimal places. Find the accumulated value of an investment of $15,000 for 3 years at an interest rate of 6.5%. If the money is A, compounded semi-annually, B, compounded quarterly, C, compounded monthly, and D, compounded continuously. So there's 4 parts to this, okay? Now let's talk about this for a few minutes. So a lot of you participate in the livestock shows, and you may end up with scholarship. You run across a chunk of money from time to time that you may not need for the immediate future. Maybe you don't need it for 3 years or 5 years. So what you can do is loan it to the bank, find out how long they need it, what the interest rate is, and how often it's compounded. And then what you'll find is when you get it back, not only do you get back the $15,000 or $5,000 or $3,000, whatever it is you put in, you're going to get more depending on that interest rate and how many times that interest is compounded. So that's really interesting. It's really important. Okay, let's figure out what these numbers mean. So this initial investment, that's your P. that is your principal, okay? This, 3 years, that's your time. And remember, it's always in years. Now we have this little interest rate over here. Now, we don't want 6.5, right? We don't want that. We're going to divide by 100, or you can move your decimal place 2 places to the left, one or the other, okay? This ends up being 0.065. Okay, so here we go. We're going to start with letter A. Letter A says it's compounded semi-annually. All right, that means we are using this formula. How do I know that? Well, it did not say continuously. So that's how I know that, okay? This told me that I do have an N. How many times is this compounded each year? Semi-annually means N is 2. So I'm gonna use this formula and I'm gonna plug in the numbers that I know. P is 15,000. 1 plus, here's my rate on top, over my 2. And then I'm gonna have 2 times 3. So I just used this formula and I plugged in these numbers, and this is what I ended up with. Now, if you have a graphing calculator, you can put this right in just like that and you get the answer. If you have a scientific, you're gonna need to take it one little step at a time. So just in case that's what you're dealing with, let's take it one step at a time. Let's just write over the 15,000. Let's write over the 1. Let's do this in your calculator. 0.065 divided by 2. 0.0325, okay? And then we'll multiply these and we get a 6. All right, one step at a time. Let's finish what we have in those parentheses. If we add 1 plus that decimal, we get 1.0325 to the 6. Okay, and now you can put in 1.0325 caret to the 6th. Remember, you've got to raise that to the 6th. That's why we practiced that on the first page. Hit enter, times your 15,000. Okay, when you do that, you should end up with $18,173.21. So look at that. If you went to the bank and this was your interest rate and they compounded it semi-annually, and this is what you put in at the end of 3 years, you made $3,173.21 for doing nothing. How about that? It's a pretty good deal, okay? What if we don't compound it semi-annually? What if we compound it quarterly? All right, well, let's try that. Compounding quarterly means N is 4. So we're going to do this whole thing again using this equation because it does not say continuously. Okay, so here we go. The only number that's changing is N. However, N is in 2 different places. N is in the denominator. See the N right here in the denominator? And N is in the exponent. So it's going to change our answer. We've got an N in 2 different places. Okay, let's do this again where we take it one step at a time. If I put 0.065 divided by 4 in my calculator, I get 0.01625. 4 times 3 is 12. Okay. If I finish up those parentheses, I add 1. I end up with that. Now again, in your calculator, we want to take this number here, the 1.01625, we want to raise it to the 12th and hit enter. Then multiply by 15,000. And we end up with a total of $18,201.11. Remember, we're rounding to the second decimal place since it's money. All right, not a huge gain, but we made more money when we were compounded quarterly. Okay, all right, let's try C. C, we are compounded monthly. All right, so again, I'm using this equation because it does not say continuously. This is only for continuously. Okay, so that's coming in D. All right, this says compounded monthly. So what do we think our N is going to be compounded monthly? 12. All right, so same formula, almost the same numbers, except, again, N is in the denominator, so we need a 12 as the denominator, and N is part of the exponent, so we need a 12 as part of our exponents. Okay, we're going to clean this up. 0.065 divided by 12 ends up being 0.0054167. I just took it out really far. You always want to take things out really far when you're doing it step by step like this. 12 times 3 is 36. All right, I'm going to add 1 to that decimal inside the parentheses. Now I'm going to take this number here, raise it to the 36th power, hit enter, multiply by 15,000, and you get, depending on how many places you carried the decimal out, somewhere around these two numbers, something around 18,220. And then your cents will vary a little bit, and that's okay. Even my math lab will let you vary a little bit on this, okay? All right, so I think I see a pattern, guys. When I'm compounded 2, here's my total. 4, here's my total. 12, here's my total. The more times I compound it, the larger my ending of balance is. Okay, so what do we think is going to happen if we are compounding continuously? It should go up even higher, right? Well, let's see. Now, here's that magic word, continuously, which means now we're moving on to this formula. So we're going to have A equals P. That's my principal, 15,000. E, that's a button in your calculator. Remember, I have a lot of students that say, I don't have anything to plug in for E. It's in your calculator. RT. R is that 0.065. T is 3. All right, we're going to take this one step at a time. First thing we're going to do is find our exponent. So 0.065 times 3 is 0.195. Now in your calculator, here we'll do it in mine just to make sure that we're comfortable, okay? I'm going to do second E. Okay, so I have my E. I'm already raised up here. It already wants me to put in an exponent, 0.195. And I'm going to hit enter. Then I'm going to multiply that by 15,000. And there's my answer. $18,229.66, which is definitely the most money. Definitely the most money. Okay, just in case you need it, let's go back. Let's do A together with our calculator, just to make sure if you need it that you have it, okay? Because some students really struggle with this in their calculator. So again, first thing I did is I took 0.065 divided by 2. This was my decimal. I added 1. There we go. I'm going to take this value, 1.0325, here's my caret, raised to the 6th, and I'm going to hit enter. Then I'm going to multiply it by 15,000. And that's how I got my answer, and I just rounded it. So if you struggle with that, text me, call me, take pictures, email me, whatever you need, and we'll get that worked out. But that is how you handle those problems. And that ends 4.1. So you are now able to do those My Math Lab problems. We are ready to start 4.2, and that'll be your next video. So I will talk to you later. Stay healthy, and I miss you.